Alright, so in today's video we're going to be talking about some of the differentiation rules for partial derivatives. So the first one we're going to start talking about is the chain rule. So just to draw an analogy for the chain rule for a single derivative, remember that we had this rule as follows. So let's suppose that we had a function y that was a function of x, and x itself was a function of some other variable t. Then in order to differentiate y with respect to that internal variable t, what we would do is we would have dy over dx times dx over dt. And then we would take each of these derivatives individually so as to get the derivative for y in terms of that internal variable t. Now if we extend this to two variables, for example, and this extends to essentially just any number of variables that you choose for your function, and we suppose that x is a function of t and then y is also a function of t, then what we would end up getting is, if we differentiate f with respect to that single parameter t, and because we're differentiating with respect to that internal variable which is common between the two, we usually just use this notation. So we use the normal df dt notation, and this is going to be equal to partial derivative of f with respect to x times dx dt plus partial derivative of f with respect to y times dy over dt. And hopefully you can see that this can extend over any number of variables that you choose for your function. So just to give you an example of how this works, let's suppose that we have f of xy equals to the following function: x squared plus xy plus y squared. And let's suppose that x is parameterized as a function of cosine of t and y is a function sine t. So the first thing you would do is you might think, well, maybe we can just replace those things into there and then simply differentiate the function with respect to t. That would be one way of going about it, but then another way that we can go about it, and that it might actually be more convenient to do it this way for more complicated functions, is to actually take each of these elements individually and then just multiply them together. So let's take the partial derivative with respect to x first. So we're going to take this expression, so that's going to be 2x plus y, and then we're going to have partial derivative with respect to y, that's going to be equal to 2y plus x. And then each of these individually, that's going to be dx over dt is going to be minus sine t. And then dy over dt is going to be cosine of t. So now we can write the expression as df dt is equal to 2x plus y times minus sine of t plus 2y plus x times cosine of t. And now what we can do is, since we're talking about the t variable in here, what we can do is we can put these two values and substitute them in here for the expression of x and y. So this would give us the following: minus 2 sine t cosine of t, because this is 2 cosine times this, and then we're going to have minus sine squared t, and on this side we're going to have plus 2 sine t cos t plus cosine squared t. And you can see that these two terms are going to cancel out, so in the end we're going to get the following. We're going to get cosine squared t minus sine squared of t, and that's going to be our derivative for that multivariable function with respect to that parameter t. And notice that we would have gotten the exact same result by just substituting these values into the first expression from the beginning, and then just differentiating this function with respect to t, because remember, cos squared t plus sine squared t, that becomes 1, and then this would be sine t times cosine of t, and if we differentiate that using the product rule, we would get back to this. So in essence, it doesn't really matter whether you substitute in the beginning or afterwards when you're substituting for the expressions into the partial derivatives. But sometimes this longer method might be more convenient if the initial expression is a little bit too complicated to work with. So it just depends on the problem, but this is just the general idea, and this can be extended to as many variables as your function has. Now the next rule that I'm going to talk about is of course the product rule, because as you might expect, all the rules of differentiation can be extended to partial derivatives, and they work very intuitively. I mean, there isn't anything very complicated about them. As long as you understand how these rules work for single derivatives, you can sort of imagine how they're going to work for these partial derivatives. So let's suppose we have a function of two variables that is in itself a product of two functions of two variables. So if we want to get the partial derivative of f with respect to x, what we would do is we use the product rule, which would be differentiate one of them with respect to that variable times the other function plus the partial derivative of the other times the other function. So that's c. Similarly, if we had partial derivative of y, that would be g of y and then times h plus h of y times c. So very straightforward. I don't think I need to show you a lot of examples with this because it's a very intuitive result. Now obviously this can also be applied. Let's have the quotient rule. So now let's have two functions. Let's have a ratio of two functions. And then the quotient rule, if you remember, it's going to be the following. So let's have partial derivative of f with respect to x. That's going to be h squared. And here we're going to have g with respect to x times h minus h with respect to x times g. And similarly, if we want the partial derivative with respect to y, we would have once again h squared, and here we would have partial of g with respect to y times h minus partial of h with respect to y times g. So that's a quotient rule for you. And the last rule that I would like to explore here is the logarithmic differentiation. So if we have a function x of y, then we're going to have the natural log of some function gx of y. So as you may imagine, if we take the derivative with respect to x, we're going to get, remember the derivative for a logarithmic function is the derivative of the function inside over the function itself. So in this case, we're taking the derivative with respect to x, so that means that we're going to have partial derivative of g with respect to x times 1 over g, which is the same as just this divided by g. And then if we want partial derivative of f with respect to y, we're going to get g of y times 1 over g. So that's very straightforward as well. Now just to show you an example, let's have the function f equals to natural log of 2x squared plus 4y squared. Now partial derivative with respect to x, gonna take the derivative of this, which is going to be 4x over 2x squared plus 4y squared. And now for the partial derivative with respect to y, we're going to get 2 times 4, that's 8. So 8y over 2x squared plus 4y squared. So you can see this is a very straightforward procedure, but I think a lot of people may actually have trouble sometimes, because obviously partial differentiation requires you to differentiate with respect to one variable at a time whilst treating the other ones as constant. So it's just a matter of practice. And these are some of the main, there are some other rules that you may apply. There's a rule actually for implicit differentiation involving partial derivatives, but it only works for functions that have a few derivatives, so like 2 variables and 3 variables. But Anything beyond that is going to be overly complicated, and in reality we wouldn't really encounter functions like that, because remember that functions of two variables in themselves represent surfaces in three-dimensional space. So you can imagine that a function of three variables doesn't actually represent anything in three-dimensional space. It represents something in four-dimensional space. And what we see in three-dimensional space, it might be just a projection. Just in the same way that if we reduce this from 3 dimensions to 2 dimensions, what we will see is the projection of this surface onto this xy plane. That's just an analogy to give you. But in reality, it's useful to know this kind of thing, because sometimes we might deal with functions of 2 or more variables, and this is essentially how you apply partial derivatives. And in the next video, we're going to be exploring this concept, and we're going to apply to finding the equation of a tangent plane at a point on a surface.